Okay, so this lecture is going to be about one of the latest features on distributed firewalling. I'll also explain some of the things that are happening, even though the lab will not include them for the time being. So let me start by, I think what's important is to explain the why before the how. So this is what I'll try to do here. So imagine you have a VNet and a few VPCs. This could be in Azure and AWS, and you have a pair of transit gateways. And let's assume that now we have, I think we explained network domains and network segmentation, which is like AKA VRF, whereby in this setup, we're going to have dev, prod, and shared services. And as we explained, whenever we attach the spokes to the transit, we can associate the spoke with one of these network domains. So you can see the spoke on the left is in dev, the one that has B is in prod, the third one is in shared services, and the fourth one is in dev. So everything looks good. And let's see, again, let's try to understand. So that now, because we have shared services as per our discussion, generally dev wants to access shared services and prod wants to access shared services. Thus you have the connection policy that connects shared services to prod and dev. And what you're seeing here is the opposite, because remember that connection policies are bidirectional. So the problem is that the granularity of a connection policy is at the network domain level. So it is not possible to limit, for example, communication within the network domain. So the problem with network domains, though they are a great feature, and don't get me wrong, I'm not saying that distributed firewalling is a replacement of network domains. Network domains are great when you're looking at the macro, at the big picture. You want to separate prod from dev. That is definitely a network domain problem, a network segmentation problem. But if you want to get granular, and again, let's look at the two blue or the two dev domains within our environment that have the instances A and D. If I were, for example, to go and launch 50 instances here and 50 instances in the other VPC, I am not able to dictate which instance in this, which instance in the VNet can communicate to which instance in the VPC. I only can do with network domains to say that these routes will be in here and the route for these prefixes will be in the opposite. So there is bidirectional routing reachability, but I'm not able to get into the granularity of which instance or which service in the VNet can communicate with which service in the other VPC or VNet. The other problem is, again, even when you have a connection policy, let's say between dev and shared services, you also have the same problem. You can envision that you have 10 instances in this shared services and 100 instances in that VNet. You're not able to get more granular on who is allowed to talk to who and on what port, and basically put a zero trust policy across your workloads. The only thing you can do and say with connection policy is you're just leaking routes between these two network domains. Thus, routing reachability will be there, but you cannot be more granular. Obviously, I'm showing a single instance in these VPCs and VNets. In reality, there could be hundreds or not even thousands of instances within a VPC or a VNet. So one typical approach is, and since we've discussed FireNet, is to go and insert a next generation firewall on that transit and put the policies on what is allowed to work, obviously add the inspection, IDS, and all that stuff. The reality is they can definitely be a solution. However, they are an overkill, especially if you're doing layer 3, layer 4. Imagine having to carry the traffic through the VPC router to the spoke, to the transit, and then to only figure out that you are denying is a particular port. Can we do anything better? This is the question. The other problem is the firewall does not have visibility and thus cannot affect intra-VPC traffic. What I mean by this is if I launch another instance in a VNet or even a VPC today, the firewall will not be able to see this traffic and thus cannot govern or stop it or block it or limit it. So these are the two problems that we see with the firewall approach. And this is why we looked and said, we already have that great data plane across the board, and it's a distributed data plane. We already have firewalling capabilities within those gateways. And what we said is, why not have a distributed firewall across wherever we have the data plane, wherever we have the gateways. So all of our gateways, in a nutshell, become enforcement points. They become a place to enforce policy. And so you can look at all of these now at the full layer of gateways, spoke gateways, as firewalls. And obviously this is better because now you block traffic very close to the source instead of having to drag the traffic to a central point. The other advantage, because you are distributed, you can have 1,000 firewalls in your network instead of having a pair of firewalls that are central. Okay, the other advantage is, what about, again, the problem that I explained, the problem in this setup between the A and E instances. We are also able to orchestrate the provisioning of Azure network security groups and even recently AWS security groups. So whenever you write a policy, the other third advantage, which I think is very important, so not only we do our spokes, we can even orchestrate the network security groups to limit this communication between instances that are within a VNet, where that traffic originally will not even reach our spoke gateway. This is another advantage. The third advantage is that it is central, meaning all what you need to do is to declare your intent, who is allowed to talk to who and on what ports. The system is intelligent enough to decide, do I go and deploy the policy on the firewall, or do I go and render it via the provisioning of Azure NSGs or AWS security groups? You don't need to think about the problem. All what you need to think about is writing the policy, and the system is intelligent enough to extend the distributed firewall not only to our gateways, but also to be able to automate the provisioning of the CSP security groups, as well as network security groups for intra VPC or VNet segmentation. So this is what distributed firewall is all about. We're also adding IDS capabilities. So IDS is already there in the platform. Today, it's intrusion detection system. We have the capability, even for those folks, as we discussed on egress, to be the egress point that takes you to the internet. So we can do things like SSL proxy. We can do IDS, as I mentioned. We can do egress filtering. All of that can happen on this, within this distributed firewall offering. So this is a bit on the distributed firewall problem statement, as well as how it works. So I think before we go that far, I'll probably go and just explain. So the idea is that before we go there, the idea is the way it works is you need to define a group, a smart group. A smart group is a way to group your resources. So you can mostly, I mean, I think what's very common is to define smart groups. We call them smart groups based on tags. So generally, if you are an organization, uh, most, I mean, it's a best practice to fully tag your resources so that you know to which project they belong, to which environment they will belong, and the more extensive your tagging strategy, the better you will benefit from smart groups. Even if you do not deploy tagging, you're still able to do things via IP addresses. However, I mean, tags have a lot of advantages. So the idea is, let's assume that, again, I'm just giving an example. Let's assume that you have a group one, or group, let's call it group front end, and a group app, and the group database. Again, I'm making it very, very simple. And you can say maybe for front end, please go and fetch all instances that have a, let's say, environment production. Again, tags are key value pairs, as well as role is front end. I'm just giving an example. So if you have these two tags together, then you belong to the front end. So what's going to happen is our platform is going to go and check the CSPs and see who meets the criteria. The moment we find an instance that meets the criteria, we are going to add this instance into the relevant group. So the end result is you're going to have different instances, okay, in the different groups. And again, the nice thing about using tags is even if you're doing something like infrastructure as code, and you provision tomorrow another instance that has the same tag, that instance is going to be directly carried over into the relevant group. Now that you've defined the tags, what's next is to define the policy on who is allowed from these groups to talk to each other, and on which ports to limit the communication. Once you define these rules, the system, as I mentioned, is intelligent enough to decide where to provision, on where to render the rule, whether be it on our spoke gateways or within the CSP platform. So this is what we are, what we're talking about. You create a smart group, and generally we will urge, we think CSP tags are the best way to do it. Again, if you want IP addresses, they are available. And you can do, say, give me like all resources that belong to BU1. Obviously, this is very simple, but if you want to do something a bit more complex, then this is also possible. You can have multiple conditions and do and or logic between them. And you can always do a manual fetching of the CSP resources, or there is a timer that also governs this if you're not doing it manually. So as a result of this environment B1, notice that we captured 3 instances. And again, if you remember our lab setup, let me just sure, okay. So in our lab setup in BU1, we had 3 instances that are in the yellow color, versus BU2, we only had 2 instances. Sorry, my bad. So again, this is not really a concept, but just as an idea, you can also govern what is allowed within a group. So this is an intra rule, which means it's affecting the traffic within the smart group. So in this case, we're allowing BU1 to BU1 with ICMP, or you can do interrule, which means from BU1 to BU2 ICMP. Again, the one thing to note is the direction. This is a stateful, so direction is also important. One important point to mention is there is an implicit deny. The idea of zero trust and the idea of microsegmentation is you know exactly what your workloads need, so you put it in policy, and everything else is basically denied for those particular workloads. So let's now look at the lab on distributed firewalling, which will give you a better feel of the feature.